Thanks for the organizers for having me here. I'm going to try kind of a new experiment with you. I want to show you the inner life of a free electron laser experiment in a moment. But first, I would introduce you to these special light sources. Yeah, in the agenda, I wanted to introduce you to European EuXFEL, but also to the other free electron lasers worldwide briefly. And time-resolved research with X-rays, I will probably shorten quite a bit on that. And I will also skip the salvation dynamics we have been working on in order to show you actually how we do these experiments in real life. Without much ado, this is just a teaser from last year, I think. No, 2 years ago, I see. We did summer schools with virtual labs, and I want to walk you through this lab in a moment. Free electron lasers came out over the past 15 years, with the first one starting on the far left of this map at LCLS. They used the old SLAC accelerator and hooked up undulators to generate free electron laser radiation. I'm going to show you how it differs from synchrotron radiation in a moment. But in short, these are intense femtosecond X-ray sources with which you can do structural dynamics research. After LCLS at SLAC, we got SACLA in no time at all. I think 2013 is when it opened up for users. And then in 2016-17, SwissFEL, the Korean free electron laser, and the European EuXFEL went online. These are, as you see in this color code, I'm sorry for the German, these are free electron lasers for hard X radiation. That means what we saw just in the previous talk, tens of kilo electron volts or so. And the lighter colors are the soft X-ray machines. Flash was actually the first free electron laser in the vacuum ultraviolet to soft X-ray domain. It opened up, I think, 2004 or so for users. And then Fermi went online, which also delivers soft X radiation around the up to 1 kilowatt of radiation. And in China, we still are waiting for the big facility that's called SHINE, and it will be a very, very intense light source. But in the meanwhile, since I think last year, 2 years ago, LCLS2 is now going online, and that is benefiting from the high repetition rate accelerators that were developed at DESY, and which European EuXFEL benefits from as well, meaning that you can deliver many, many pulses per second, while all the other machines that we have are always on the order of delivery of 100 hertz, sometimes a little bit less and a little bit more. And only European EuXFEL delivers up to 30,000 of those X-ray pulses per second. And LCLS2 is aiming for, I think, around 100 kilohertz repetition rate. So this is all to make experiments that are otherwise hard to do, that you can accumulate and get more statistics as well. European EuXFEL is, with this, 30,000 pulses per second, the most intense X-ray laser on this planet at the moment. And will probably be overtaken by SHINE, but that's further in the future from now. In the international context, you can see now the photos of some selected free electron lasers. I don't have a photo from PHotons, which is on the bottom right, but it looks like this next to the Pohang light source, the synchrotron. And you always see in these environments, always a synchrotron nearby with the X-ray infrastructure that is needed. So here's SACLA, where we do experiments at the far end near the near the synchrotron storage ring. LCLS has also SSRL hidden underneath synchrotron, and SwissFEL also has the Swiss light source next door on the other side of the river. The longest one, these are all up to 700 meters long facilities. Only European EuXFEL is the longest one with 3 kilometers, 3.2. It starts here in this congested area called DAISY with many biophysical, chemical labs. And the big Petra storage ring, of which you see an arc sector of Petra 3, which is now undergoing in the future to upgrade itself to Petra 4, which will have a few more arc sectors implemented. On the bottom top right, you see a very short linear structure. This is flash 1, and there's also flash 2, not on this photo, a little bit to the right, because it's so successful machine, and it was the test machine, the test facility, to see if this accelerating, superconducting accelerator structures work for the hard X-rays, which are in this long, 2-kilometer long accelerator section. So we have this linear accelerator stuffed with these superconducting modules, accelerator modules, a switch yard where we go into a maze of tunnels, up to 5 we have. 3 are now fully operational, 2 more to load. And the beam lines are then in the so-called, in the experimental hall in Schenefeld, an underground laboratory, which has the precise size of a commercial football soccer field lying out there. And yeah, this is now a photo, also a little bit older, because all the buildings that are now dotted in exist and are feeding, serving food. Here is the main office building in this O shape, and underneath, exactly underneath, are the receiving 5 tunnels that enter scientific instruments or beamlines that we have there. This is more or less a sketch how it would look like. We have in blue the electron beam. So it went past here through XTL on the left. That's the 2-kilometer long linear accelerator. Switch yard for electrons. These lines, dashed lines, are undulators that then produce X radiation that then feed one tunnel for 2 instruments, another tunnel for 2 instruments, and the third tunnel and the third undulator for actually now 3 instruments. This is a little bit outdated, this graph. And that means that with inauguration of European EuXFEL, the amount of beam time available almost doubled worldwide, because in principle, you could say European EuXFEL as of today is 3 free electron lasers, because it has 3 independently operated undulators, and they can all be fed with these electron bunches that are produced on the DAISY site and accelerated. This is just a very short sketch of what is special about free electron laser radiation. Could easily take a whole course to understand that. But the idea is undulators, like in a synchrotron as well, emit spontaneous light. And this light, there's always one special photon somewhere in the first 10 to 30 meters of the undulators. I should mention, yes, well, at synchrotrons, we have a few meters undulator section. At a free electron laser, we have more like 100 to 200 meter long undulator sections. And in the first 30 meters, there's one spontaneous photon that goes exactly down to your experiment. And this one will then be successively amplified. There's this funny thing with the microbunching, which is a consequence of the radiation produced. And at the end, we got more or less all the radiation we can possibly get. After saturation, we have equal probability for absorption and emission processes, so we don't really gain more light, but we get a lot of light. And how much light we get? Well, first, what's the difference between a synchrotron and a free electron laser? I usually tell students it's the three pillars of excellence or so, which is intensity, time structure, and coherence. I will not talk about coherence today, but intensity and time structure. So this is more or less a comparison of Petra 3 on the left and European EuXFEL on the right. And the undulator radiation, which is spread out due to the RF cavities mainly, out to 100 picoseconds pulse width, they can deliver in those few meter-long undulators, let's say up to 10 to the 9 photons in a single electron, from a single electron bunch. This is different from an undulator, from a free electron laser with its 100 times longer undulators. There we get on the order of up to 10 to the 13, depending on the X-ray energy. It's, hard X-rays, it's a little less. That is 4 orders of magnitude more light in a single pulse. The electron bunches, interestingly, have the same number of electrons at synchrotrons and at free electron lasers. So you could roughly say that a synchrotron undulator emits incoherently, but now more coherently at the ESRF and so. So if you have 10 to the 10 electrons and 10 to the 9 photons, that would mean that 1 photon for 10 electrons is working for your experiment. And that's what you get if we just do a simple math. 1 meter long undulator gives you 10 to the 9 photons. And now we take 100 meters long, so 2 orders of magnitude more, but we get 4 orders of magnitude more light, the 10 to the 13, coming out of a free electron laser. And the electron bunch has been compressed down to femtoseconds. So here, this is a little outdated. 2 to 100 femtoseconds is the usual size of an electron bunch, and that's of the X-ray pulse. But meanwhile, there are schemes successful and demonstrated that can also generate attosecond, sub-femtosecond long X-ray pulses. That is very fascinating because now we are also entering the attoscience world with free electron lasers. This is one science case of the several that exist, and this is more or less going towards like a molecular movie where you have an optical pulse that excites the system of interest, and then vibrations, excited states, pathways are accessed, and you want to see what is the molecule doing, how does it change structure or so. And that you can do, for example, by X-ray diffraction. But there is this caveat on the left, you see it, that's an old simulation that was done after you pass the X-ray pulse through the, let's call it protein in this example, it blows up because you ionize many electrons. You can ionize almost carbon, you can ionize down to the last electron. And so you get a Coulomb explosion afterwards. And the idea is that, but just before they move apart, the X-rays pass through and gave you a correct image of the actual structure of the system. And in a kind of pump probe scenario, as sketched here, you would then be able, if you change the delay line, to stitch something like a molecular movie. And I put the right simulation just to make clear how in motion even a cup of coffee is when you let it stand next to you. There's another interesting difference between free electron lasers and synchrotrons, and I noticed this when we did our first experiment and we had some leakage of X-rays going through, and I put lead tape to block the X-rays, and I thought everything was fine. But then when we turned on the beam again, everything was fine, and after a few seconds, we had the same noise again. And this is a photo we took at the beamline I actually built called FXE. And you see the blue nitrogen fluorescence that is stimulated from the X-rays entering in air. If you focus this X-ray beam to below 50 microns, then you can go into a steel block. And if you wait a little bit, you see on the other side the beam coming out again. So we can drill holes through anything. So free electron laser radiation is really dangerous and also caused quite some excitement with the radiation safety group because they were worried about the radiation protection walls. And so we had to set up schemes to never ever be able to focus the EuXFEL beam into the wall. Air is good. If you have 10 meters of air, that takes care of the danger already. But keep in mind, a focused FEL beam drills through anything. There's no material that will survive. And we also drilled through 30-centimeter thick copper blocks in less than a minute. So it is very special, this radiation. This is more or less my motivation, my personal motivation. And the question that I asked myself when these free electron lasers were being built in the first part is, could we ever see a molecular movie of something as moving around like you see these water molecules bouncing around? And will we ever have a chance to see it like you see here? So the simulation you see on the left, we would actually like to see in a movie with real molecules. The answer, I don't know. If we will ever be able to see what you see on the left with measurements. With simulations, it's easy. But my feeling is if we ever had a chance to do that, we probably need a lot of light. And that's exactly where free electron laser radiation excels. And so that is my personal motivation. I will skip this example. If we have time afterwards, so I can go back, but this is a molecule which undergoes different processes in solution, like you saw before in this water, and we can generate different charge and spin states and monitor which pathway we prefer, which we cannot do optically. And so we did this at a free electron laser, but I won't bore you now with that, and use the arsenal of X-ray observables. And in order to see what is going on in the system, and that is our first attempt to see something like a molecular movie of a violently reacting molecule. But I will skip this. I will also skip my salvation dynamics. This might be the idea behind structural dynamics research with X-rays. And this goes in both directions to synchrotrons and to free electron lasers, depending on the time resolution you can work with. So for femtoseconds, of course, we need free electron laser radiation today. This is an example where you can see a molecule on the left. It's a test molecule, you could say, or model sample, where there are different processes occurring that we know from optical femtosecond laser spectroscopy. So we use the best tools we have to get the job done and the easiest ones while doing that. But what it doesn't do is tell you, for example, about the spin state that the system is in, and that we could use with X-ray emission spectroscopy. The optical studies do not show you what the molecule is, how it's changing its structure. This we can do with X-ray absorption spectroscopy, but also with wide-angle X-ray scattering, here abbreviated as diffuse scattering. And the diffuse scattering might even be able to look at the solvation shell around the reacting molecule to give a first new, more modern insight into what solvation dynamics is about. This on the right is another example with Sophie Canton and Willy Sundström we did many years ago, where we optically excite a charge from the ruthenium metal. It goes somehow on the ligand system over a bridge, and then it runs into cobalt and forces a low spin, high spin conversion, which we can now measure with different cameras. So what we would like to have is a camera looking at all aspects of a chemical reaction. And so one for electronic orbital changes that we can do with X-ray absorption and X-ray emission spectroscopy. And spin state changes works also with spectroscopy. Internal structural changes can work with wide-angle scattering, but it also works with EuXFELs. If you get the signal quality at a free electron laser, for example. And the wide-angle scattering would be for external molecular guest-host interactions in the liquid. So we would like to have different cameras looking at different aspects of the ongoing reaction. And this would then tell us how the molecule proceeds and with what efficiency, or why it does things with more or less efficiency. This is now a case example, very old, that we did a long time ago, where we have a transition metal complex. In blue is the ground state, and when we excite it, it expands to the red structure. And that is when it goes to something that is here identified as quintet T2 state, or the high spin state. And we identified, actually, that's now 15 years ago, a new configuration coordinate, which is the distance between the central metal and the nearest neighbor ligands. While in chemistry, we usually just use the x-axis as Q, meaning it could be a vibration, or a isomerization, or it could be a distance change, or both together. Here we can actually measure with physical precision the geometric structure of the ongoing reaction. And I will skip this, but this summarizes that we have to know what is going on with optical laser spectroscopy. And so on the graph on the left, all the numbers with timescales you have is what we learned from femtosecond laser spectroscopy. But what we don't know is what's going on. We don't see what's happening really in the molecule. And for this, we use then the X-rays, where we can use either X-ray absorption fine structure. This is kind of before-after measurements that we did in blue and red. So you see differences in the EuXFELs and also in the xanes. And more interesting for internal spin states of the transition metal, we can use something called X-ray emission. And this I want to show you in a moment. This is too complicated. I will skip this, but this is how well we are doing X-ray absorption spectroscopy, stepwise improving the time resolution and also the overall data quality, so that we can eventually see even vibrations in the molecule occurring. That's pretty fascinating. And this is something that I will keep flashing to you now, because that's what we will be doing live in a moment. So on the top left, you see reference compounds that exhibit different spin states. And you see the so-called X-ray emission spectra, which comes from the 3p orbital, changes its structure, let's say, depending on what spin state it is in. And we can also see things happening on much faster time scales than just before and after. That's you see here in this example. Something is different after 50 femtoseconds than after a picosecond. And these changes are indicative of the excited state pathway that it's taking from the initially excited state down to the final state, this simple photophysical reaction. And that's where I would switch screens if you allow. So how do we do such a study? Yeah, so we are now in entering VLab. So let me open up. Okay, we can go back and you see a typical X-ray control room where you have all these screens, and there you have a physicist who always wears a white lab coat in the control room, and he's looking at some data, in this case, diffraction data. There's also a fridge, and we can now walk into the X-ray hatch here. So now I will open the door, and we enter the X-ray hatch, so you can take a look around, and you see the whole beamline in all its glory. And uh, we actually have in the real instrument also a poster on the wall which shows you what's behind the 1 meter thick concrete wall. So I can just bump in, bam, I can go through. And that's the X-ray tunnel for the X-ray delivery. And you have all these devices here, which is pretty cool. And you can actually open them up to take a look what is going on. So you can drive these devices in and out. These are actually refractive lenses, beryllium lenses that are placed in with different fillings, and you can put them in or out of the X-ray beam. Now, the only problem we have here is that we see nothing. There are no X-rays. The screen is completely dead. So the question that I give students is always, why are we not seeing any radiation? This is just a little fun fact that the software allows you. And I always go in this position. I say, why don't we see X-rays? And then you should wake up and say, because the X-ray door is, we have to protect the lab coat guy. So then we close the door. Okay, now we are in the X-ray hatch with X-rays, but we are an avatar, so that's okay for us. And now we can go and see the beamline. Now you see pulses and so forth. And you can go around and look from different sides. I already pre-aligned a little bit, but I will just walk you through starting from the undulator. So that's 1 kilometer upstream. And this is one of these 5 meter long undulators that European EuXFEL has. And you see the ants marching in. Those are these, in red, you have the electron bunches that are going in, and you can see the X-rays. This is just an animation. We haven't yet made gap scan and all this. This we didn't have money to include yet to the simulation, but you can get a picture. And they are in an air-conditioned enclosure, and this goes over almost infinity, 200 meters downstream, where you can then guide the X-rays to the experiment. Now we will go to the tunnel almost near the end of the, just before the X-ray hatch. So that's the whole travel, 1 kilometer. So you see the same concrete wall now from the other side that I showed you before with the poster on it. And here we have a 4-bounce monochromator, which is not in yet. We can put it in. And then we, yeah, it's not much yet, but the math is correct. I'll show you in a moment. So that's just one of them. And then we have the second downbound. So it's a 4-bounce monochromator. I will just go one further. So just to give you the idea, because we work with students and PhD students and partially even postdocs in summer schools and also in lab courses with this software. It works actually very reliable. And they are supposed to measure stuff here on the left in this empty screen. So we want to put it at live. But it means that when I click on the top left where you see monochromator, I see all the devices we virtualized from upstream to downstream. So it starts from the undulator, goes to the sample environment, and even behind. Yeah. And then we also have on the right the detector that we're looking at. So we have to know what we're doing, and then we have to pick the right detector to get the data on the screen. In order to do that, I will go to this diffraction grading quickly, which you see here. It's not implemented, but I can insert the grading now. That's diamond grading, I think with 100 nanometer spacing of the grooves. And you see now 3 balls coming out. Those are the plus minus first order and the 0th order beam. Plus minus first order should be only 1% of the intensity of the 0th order. The goal is that we beam split it here in order to be able to do diagnostics with diffraction order beams without influencing the experiment itself, so that we can do this all in situ. So I go now one further, and this is our first device that we have here. It's hard to see. Now you can barely see. So there's this rotating thing. You see it, the arm coming down. It's a helium-filled tube with a strip detector at the end. And the goal is that we want to put in a curved crystal. Yes, and I have to take it out for a moment. That's a little bug. So we select a crystal. Right now we have a curved diamond crystal. And we can insert it, and it will diffract out the first order beam. So the one on the right, 3 bolts going in, 2 bolts going through, right? So we're picking out the first order that is going here. It's hard to see, but you might be able, where the mouse is, you might be able to see that there should be a crystal, a curved crystal, a diamond 111 crystal. Now it has to be adjusted to the Bragg law, and that currently is happening in a funny way. I have to know the X-ray wavelength, and then I have to adjust the height such that magic can happen. And now you see magic happening. You see these rainbow cakes flying out, right? And these are the dispersed different wavelengths that get diffracted, Bragg reflected from this curved diamond crystal. Now, in order to measure something, we have to swing the arm so that we somehow get some light. Aha. And if I swing too far, it goes away. And if I come back, I can put it roughly in the center. And now pay attention to the y-axis on the top left. There you see the intensities are fluctuating. So this is always auto-scaling. We might change this to make it more alive. And it looks pretty boring, what you see here, right? But for the students, we have always the Save button on the top right, and they can download the data for post-analysis of what they're doing. That this looks so boring is because I just turned on the monochromator for you. So let's look at the spectrum of a free electron laser. There you go. That's it. So now I can go back to him. And this is indeed the spiky self-amplified spontaneous emission spectrum. It is a property that makes a physicist extremely unhappy because it doesn't look like these laser pointers that we're used to, where everything is smooth and monochromatic. But it has many spiky structure in there, and that comes from the process of the light generation. And there are schemes now around that other schemes that are called self-seeding and so forth that make it more monochromatic and more intense. But the monochromaticity here, when you download the data and you analyze it, you find out at 9,300 electron volts, the spectral width is about 30 electron volts. And so it is quite monochromatic. Now only a factor more more monochromatic than, let's say, ESRF upgraded diffraction limited storage ring, but earlier it was an order of magnitude more narrow than an undulator at a synchrotron. But we now have this radiation, and we can then go further downstream to the next device. The next device is the so-called time arrival detector. That is something that we have to pay attention to when we work at a free electron laser with femtosecond radiation. The problem here, or the issue that we are solving, is that we have two independent light sources. We have an optical laser somewhere in the hatch next door that produces femtosecond pulses of light to excite your molecular dance. And then you come in with the EuXFEL radiation that is produced 3 kilometers upstream at the photocathode in front of the linear accelerator. And then there's a linear accelerator, and then there's a tunnel temperature that can make the 3 kilometers a few microns longer or shorter. And that means it is inherently difficult to synchronize those two pulses perfectly. And perfectly means to better than a few hundred femtoseconds. A few hundred femtoseconds translates to the thickness of a hair. So if you change the path length of either source by that much, then you get this jitter. We are interested to measure with better than 100 femtosecond time resolution. And for this, we try to stabilize, and there's a very complex scheme that's actually quite good at European EuXFEL, but also elsewhere, that tends to stabilize the repetition rate and the arrival time of both pulses to well, a little bit better than those 300 femtoseconds. To go beyond that, to measure more precisely, we had to bite in that apple and say, well, maybe we could measure the arrival time for each pump probe shot. And that is what is being done here. So what you kind of see illustrated, let's see if I can make it more visible. Well, you see these square-shaped red rectangles flying in. They are right now representing a femtosecond flash from the optical laser. They are going at an angle onto a surface, which is, in this case, a diamond plate. And the X-rays, which is here the leftmost pulse, still simulating everything, that EuXFEL pulse goes through the diamond and generates a few, well, a lot actually, of electrons in the conduction band. When electrons are in the conduction band, naively spoken, it looks like a metal and reflects the laser light much better than before. And that would then mean that the reflectivity or the intensity of the light that is here, let's see, this is all nuts. I have to zoom out, maybe. Yeah, I think it's it's not easy to see, but one should see that actually the rectangles reflected, they have a lighter and a darker color, but it's for some reason that's not visible right now, at least not for me, but it would be different. And that is because when the EuXFEL came onto this onto the diamond plate, That's when you get the instantaneous excitation to the conduction band, and the angled optical laser, a portion of it already transmitted through before the X-rays came, and the other portion comes through when it after, and that is then reflected higher, and so you get a contrast that you can image on a simple CCD detector, where you see then what you see here, a low intensity and an edge to a high intensity. And right where the EuXFEL beam strikes the diamond plate is where this transition takes place. So we can then, with simple math, we can calculate the relative arrival time, and you see that this edge is bouncing back and forth on this screen. And that is, I think it was historically also the first timing tool that was implemented at LCLS. Meanwhile, there's another tool around where you implement an optical spectrometer. So that's this one. And so the idea here is that we take the femtosecond laser pulse and we chirp it. Chirps means that we put different wavelengths at different positions over a picosecond or so. Red in front, blue in the back or so. So this image is wrong. We have to correct it. It has to be reversed, but you can do it either way. And now you can see that when this picosecond long, colorful chirp pulse goes through the diamond, and the X-rays are in the middle, in the center, then the reflectivity of this specific color changes. And that you then record with a spectrometer, and ignore the x-axis that is wrong. It should say optical wavelength in nanometers, where we then can see how the intensity of the light changes as a function of the X-rays flooding the conduction band with electrons. And you also get this jumpy thing. This is now standard. I wanted to say annoying, but now meanwhile we all work with it and it works actually fine. So this is another experiment before you do your actual experiment, in order to get a more precise measure of your arrival time. And that means that when we record later in our experiment a signal, a rising signal at time 0, we get it smeared out to 300 femtoseconds. But since we know for every shot where they actually relatively belong to, we can post-sort the arrival time of each probe shot, and we get a much sharper rise time. And this was demonstrated for a diffraction experiment where optical phonons were produced. And when you didn't have the timing tool sorting out the arrival time, you just saw a step function. And when you sorted all the data, you suddenly saw ringing and vibrations on it. So that is an idea for how these timing tools, or how we get actual femtosecond time precision in our molecular dance movie experiments. The actual timing tool is actually not here, but it's at the back behind the experiment, just as a little detail. Now I can go one step further, and we get the power slits. Hard to see, but you see that the X-rays are kind of going in between. So in contrast to whatever JJ X-ray slits at a synchrotron, which look almost like those at in an optical spectrometer, so razor blade almost shape. Because of the high intensity where I showed you before we drill through any matter, we use pistons for slitting the beam. And so here on the right, you see the top piston. Let me open it up, and you see him move out. And I can do the same with the bottom one. And I can also open, that's the wrong way, I can open the horizontal slits. and that's how you get it out. Now, there is something that you notice, namely you see nothing. Um, and that is my fault because let's see, power slits. Yes, here we have the solid attenuators, and I already put in a few of them. So we have here these rods where you might be able to recognize different thick foils that we can push in and out, and we can attenuate and the beam that way. I will take a few out just to see what happens, and then you see um, the X-ray beam, and one more out, and you see something that for the students this is quite frustrating because you see a white central spot, and the question they always get is how big is the beam? And when you download this data, what you get is a top hat because the white color represents saturated light. And so you have to attenuate the beam appropriately in order to get the true Gaussian shape of this beam. You also see that it's bouncing around. That is indeed something we are working on at European EuXFEL to remove. There is the mirrors in the tunnel, which I did not virtualize yet. They deflect horizontally, and if they wiggle a little bit because of our long arm of 800, 400, 600 meters, wherever the mirrors are, we are more likely to see beam deviation positions than like at a synchrotron with their 10 to 50 times shorter distances. But that is that. I will just put in the guys again. 1.6 and 3.2 for a special reason, because we also have these lenses where we have nothing in. There's something because we wanted to also teach the students a little bit respect for the X-ray beam. And so this is now the sample, which is in our case a liquid jet. And in red, you see the laser balls flying and the EuXFEL probing pulse. But that's not where I wanted to go. I want to go to the X-ray eye. So we first have to figure out what we're doing, what's going on. And for this, we insert an X-ray microscope, which is just a scintillator foil in a camera. And that was my fault. I should have turned off the laser. I already overlapped them before the session, and now you see what I was talking about. The students now have this ugly black spot in the center, and that now we can go back to the lenses. And I pick the right detector. And now I can see what happens if I focus a little bit. Yes, it's getting smaller. Now you see why I attenuated the beam heavily. And if I go one step further, I know the settings of my lenses. Then if you look carefully, you might see a white spot poking out on the side a little bit. But I destroyed the screen already. And so we learn that we respect our equipment. And the only way to get rid of this is I have to go out of the whole program and start from scratch. And so this teaches users also, okay, maybe I should think first before I press buttons. Because in an earlier version for students, we didn't have this, and the students said, "Oh, I was just hitting all kinds of buttons and didn't care." And now they care, because otherwise they wouldn't get to see it. So if I put in another lens, then you see now the saturated beam, and it's not so well focused on the center. But trust me, this was already a pretty good focused beam. So once we have that, on the sample, we know that we are focusing the beam. Then we can take this out again and mount the jet and operate it. Now we only have to know, are we hitting the the liquid at all. So we have to get an X-ray signal. And that can be done with, think. Yes, I go into this menu part where I have and I have to look at a detector, and I will be looking here at the forward scattering detector, which has something interesting. Everything is calculated. So you see the diffuse scattered light, and we can also go to the stage of this guy, and I can move him, for example, closer, and I get more Q range, or further away. And that can also have him radially integrate those rings. Then you get this figure, and if I go closer, you get more, and if I go back, you see less. So that's actually pretty cool. Now I have an arbitrary signal amplitude of something like 10 to the 12 on the y-axis, so I pay attention to that. And I go back to the sample environment, I select the right detector, I get the signal, and now I can move around, and I see, oops, I'm now losing intensity. It's now at 10 to the 11, and now it's 10 to the 12. And it's 4 times 10 to the 12 and so forth. And now it's 5 times. And since I did this before, you can trust this is the overlap position. Now that I know that my X-rays are hitting, I would have to know if my laser is hitting. And for this, I would then go back again to the X-ray eye. That would be the first one. And check the laser. So for that, I would go to the laser, and I can move his position. I already did it for you. Of course, the laser is turned off, so we give him some intensity. Yeah, and there you see him. So I can move him around, and at the moment, 0 is the good position, but that will change for students. And it's a fairly weak intensity right now. So usually we work with 10 or a little bit more, 50 micrometers. I can select between different wavelengths. I won't torture you through that, and also change the focal, the focal spot size of the laser. Once I know that my laser is hitting and I saw that my X-rays were hitting, then I am ready to do the experiment. And the experiment was what I showed a moment ago. That was the X-ray emission experiment. So what you see here is yes, you should see those circles moving out. Those are supposed to be isotropically emitted X-ray emission. Yeah, and one of them hits this crystal. That's the one we virtualize, and I already pre-aligned it. If I use a different cut of the crystal, then I lose everything, and my signal is gone. And so I have to use that. I have to also align the angle. So if I rotate a little bit, then you see I'm losing the signal again because I'm coming out of the Bragg condition for the X-ray emission light I'm looking for. I could possibly go very steep. Let's see if that works. Because we also virtualized, there you go. That is the incident light, which has a much higher or shorter wavelength, and that's different Bragg condition. And so that works as well. But let me just go back to the X-ray emission angle. So these things have to be calculated, and then you can dial them in. Let's see where it was. Here it's coming. Okay. And there's another coolness factor. I already pre-aligned everything for you, but if I turn now the 2D detector, this is what you actually would see when you look at the CCD image. And if I move the detector a little bit away, ah, cool. Uh, at least I think it's pretty cool. And so you can play around and it gets widened. It's not perfect geometric optics because we should get a bow tie if I rotate um, the from the side, right? If I rotate that way. That still not in there, but it's already pretty cool. So you can already get the X-ray emission, the energy dispersive range is then on the vertical axis, and you can then get here the X-ray emission spectrum. Then we can look at the difference. And difference means if you count, you see that the X-rays are at twice the frequency as the laser. So we can always do pairwise subtraction. And at the moment, we see no pump probe signal, which is sad, but it's usually my fault. So let's go back to the laser and we look at the right detector. And I give him now, let's say, 50 microjoules. Let's see what happens. Okay, it's hard to see, but you might think that something changed. In the center, you see something dipping out. It's really, really noisy. And yeah, but then I remember, oh hell, I attenuated the beam like hell. So I go to my attenuators, I keep a look at this, and I take out and then I get a very nice spectrum. Um, this is more or less realistic. Let me make it a little bit noisy. Yes, that looks better. It's more alive. And we can go now to the laser and look at this transient signal as a function of time delay. So I can now dial in like 1,000, a picosecond, and then I see that signal. And if you just pay attention to this little shoulder on the way down, that is below the zero line that we have here, correct? And if I go back to 100, let's see, femtoseconds, then it is there, but I don't really know where time zero is, so I can go to minus 100. And then I see this, but it's very noisy. We are at the onset of the signal, but I can also accumulate the signal. And there, students learn this square root pain. When you want to get the error bars 10 times smaller, you have to measure 100 times longer. And that's what you would eventually see going on here. So that would be more or less the laser setup. We haven't fully virtualized the path. We know where it is, but we didn't put the balls walking through. But you can see basically all this in action. And yeah, so you can look at the forward scattering, you can look at the sideways X-ray emission, and the signal quality is kind of realistic according to your adjustment. So if you screw up, then you don't see much. We also did another experiment that I will show you just briefly, and then I'll stop, I guess. I will hide the chamber. I will go out. And this is now, I have to pick the right detector. This is meant to be a scattering experiment, a powder diffraction experiment. So we can pick one of those nanometer thick film and shoot. Let's see what happens. This is still, and you destroy it, and then you get a diffraction pattern if everything was fine. The problem is it doesn't really work that way. It shows you already the results. So we still have bugs in there, but you get the picture hopefully, and you can also radially integrate, and then you get here a signature of a powder. That's very sharp Bragg peaks. And if I start delaying, you see it melting. And if I delay more, you will see it re-solidify. So this is now a nanosecond or so later. And if I go shorter, it's totally liquid and will probably blow up. And now we're at a picosecond. So after a picosecond, you start seeing melting. So we also have this experiment virtualized. We're in the start of that. So one can do quite a lot with this whole arrangement. Originally, the idea was to show the beamline in action with all the whistles and bells floating, but meanwhile, thanks to the pandemic, it turned into a full-fledged virtual experiment. We also have equipment on the back here, where we can also see some, but that is still not really implemented yet, but it is also a spectrum analyzer that we have at the back. And the idea was we had one up front, which you saw in action, and the one in the back. And if you put a sample in between and the spiky spectrum, after a single shot, bam, bam, you would get some intensity measure of the absorption edge, for example. But if you do it 1,000 times or so, which only takes a second at European EuXFEL, then you would get a true Xane spectrum in transmission mode, possibly. But this hasn't been set up yet. Timing tool is now in front of him in the real thing. And there's also a gas detector to truly monitor the intensity, but that would be more or less where we are. There you go. This is a time-resolved X-ray emission experiment. This is the difference, and this would have been the K-beta emission signal that has an intensity that is also reflecting your sample adjustments. I guess I will just stop here and thank you for your attention. Yes.